So welcome to the revision video for iGCSE Physics. This is just one whole topic. There are some more videos which are individual subsections, but this is for if you finish the entire topic. So there are 8 videos in the series. If you like and enjoy, please subscribe. Okay, so this is an iGCSE introduction into 7b, radioactivity. So quantities, we've got the idea of a becquerel, defined as the activity of a quantity of radioactive material in which one nucleus decays per second. Becquerel is therefore equivalent to what we call the inverse second, or per second. So it would be number of nuclei that change per second. We sometimes use the idea as well of the sievert. Sievert's the amount of energy you might receive from a dose of radiation. And the units for that are joules per kilogram. So it's imagining if your body received so many becquerels of radiation, you could convert that to how many joules you've received per kilogram, which is a good comparison because everyone's a different size. So that tells you really how much energy that you've received, which is often used in industry. You might also see millisievert or millisievert, which is 1 times 10 to minus 3 sieverts, or it could be millibecquerels. But you've got the two there. Typically, it's about activity. They occasionally have questions where they talk about the sievert, but you're not really expected to know sievert off the top of your head. They give you a little bit more. We should know our atomic structure from chemistry, so atomic mass number A, Z proton number, or number of protons, atomic number. 88Z is the number of neutrons, because we know that not all atoms have the same, like this one does, but uranium clearly doesn't. We should know how to use the AZX notation, and we should know all the symbols, so neutron, proton, etc., electron. Alpha, beta, gamma. So if you have radioactive decay, we get alpha, beta, or gamma emitted. Often, when we've had a beta particle or alpha particle emitted from a nucleus, we also get gamma, but sometimes we just get gamma. It's a random process. We can't predict when it's happening. We can't affect when it happens. It just happens. Also, atoms or nuclei may be split and produce neutron radiation as well. All of these particles always can damage humans or can be useful in industrial or medical processes, which you should know some examples of. Geiger tubes then, so what do? Well, they detect ionizing radiation. It enters a tube through a thin Mysia window. It ionizes gas and that produces an electrical current which triggers a count on a device. And you've got a difference in potential, maybe 0 and 400 volts between the electrode on the middle and the outside. That's what helps to trigger off that count. The background radiation, you should know that radiation could be man-made or natural. All of that adds up to the dose from the environment we live. So you've got stuff from rocks, gamma rays from the soil and space, you've got cosmic rays, you've got medical and x-rays, you might work somewhere in a power station, you might be fallout from nuclear weapons programs, you could have discharge from a nuclear reactor, and you could just go on holiday. So you do get quite a lot of radiation just by going on a plane. Cellular effects, you should have a good idea about how you can have accurate repair, inaccurate repair, or cellular death. So there are 3 things typically, and if it's inaccurate, it may grow into a tumor, which is a cancer, which could be treated by medical process to do with alpha, beta, and gamma. So actually, alpha, beta, gamma can cause cancer, but you can also kill cancers with another focused treatment of radiation. There you go, that's 7b radiation. Okay, so this is the second part of the iGCSE introduction to radioactivity. It focuses more on sort of properties and half-life and things like that. So we've got, first of all, penetration power. So different radiation will penetrate differently due to their nature. So some are particles or waves, and it depends as well maybe how much mass they have and how much charge they have to how much they ionize. So you have alpha, that will generally be stopped by air or some paper because it's quite highly ionizing, so it ionizes the atmosphere. Beta, smaller particle, fast moving, penetrates through the paper, but generally stopped by a few millimeters of aluminium because it's also quite ionizing. Gamma passes through both the paper and the aluminium because it's a wave. It's very penetrating and it needs a lot of centimeters of lead or many meters of concrete to absorb most of it. But they can still pass through even really thick concrete because it's got no mass, no charge because it's a wave. You should know about this properties table really, which is you've got your symbols, so alpha, beta, gamma. You've got the masses, you've got the charges, and you've got charge to mass ratios. So I've just taken the charges, so +2 divided by 4 relative masses gives me plus a half. The beta particle is -1 charge divided by 1 over 18/40th, or it could be 1 over 2000, which gives me a charge to mass ratio of -1840, which is huge, which means it's affected a lot by magnetic or electric fields, i.e. strongly curved. This one curves, but this one's zero. Zero charge, zero mass. Paper or skin is stopped by, for alpha, so 10 centimeters to 1 meters of air. Aluminium, we said, or 10 meters of air. And gamma, thick lead, or 30 centimeters of concrete. And the ionizing power, as you can see, are a lot, a sort of a medium, and then not very much at all. So we definitely don't want to use alpha inside the body because of the ionizing problems, but beta we do, and gamma we do, because it's not as ionizing. But alpha outside the body is particularly safe. Just don't get it anywhere near your nose or eyes. Nuclear equations, we should be able to write out the 3 nuclear equations, but remember, we could have any atoms here at all. So what they tend to do is they want you to know one of the missing numbers or 2 of them. So we're talking about all of the numbers at the top should add up, all the numbers at the bottom. And you should be able to identify alpha to gamma for each equation. And then radioactive waste. So ionizing radiation, that causes problems which arise in the disposal of the waste, which has lots of risks, needs to be managed. You should have an idea about what to do for maybe like a 6-mark question with different things with different amounts of radiation. Half-life time, we can't predict when the nucleus of one particular atom will decay. It's a random process. However, we can plot a graph to show the time it takes for half the sample to decay is a fixed time for each isotope. And in this case, it's every 2 days. So we start off with 80 counts. So that's not the number of atoms. This is just activity. So 80 atoms or nuclei are decaying. And so after 2 days, it's given out 40 particles. But then after another 2 days, it's only given out 20. And so we get this really cool graph, and we can pick a half-life. You should be able to do 3 little checks like that to work out a consistent half-life time. So there you go. That's half-life. And that's the last bit of 7b. Okay, so this is section 7c of the iGCSE introduction topics. It's fission and fusion. So first of all, let's just talk about neutron radiation. So neutron radiation consists of a free neutron, usually emitted as a result of spontaneous, i.e. it just happens, or induced nuclear fission. They can start off a nuclear bomb or a fission reaction. Obviously, these neutrons travel around and can be dangerous. They could travel thousands of meters in air, but can be stopped or blocked by hydrogen-rich materials such as water or concrete. So what happens, or what's the use of all this? Well, in nuclear fission, in a nuclear power reaction, we use a reaction called nuclear fission, and 2 isotopes in common use for nuclear fuels are uranium-235 and plutonium-239, which you should know. And what happens is the nucleus splits into 2 smaller nuclei, often krypton and barium. So there's a ratio of about 2/5 to 3/5 in the split. They are radioactive. They release generally 2 or 3 neutrons, which are released into the environment. And energy is also released, and the additional neutrons that are released may hit uranium or plutonium nuclei further in the fuel rod in a nuclear reactor and cause them to split. And we call that a chain reaction. So these atoms are splitting, they're releasing energy, and the energy is in the form of kinetic energy. The neutrons slow down and they give up their kinetic energy into a thermal energy store. Now, we've also got to know all the different parts of a nuclear reactor. So we need to know about fuel rods and how they're a source of fuel. So they're the thing that splits. So it's a non-renewable source. There's a moderator in there which slows down the neutrons, which helps them meet another uranium atom. So it increases our probability of creating the fission process. That's often made of water or a block of graphite. You should know that. Control rods, they dip into the core of the reactor. They absorb neutrons, so prevent them splitting down into more atoms and slows down the process. So often they're made of boron, and a shield that's made of concrete or steel with thick layers to absorb the radiation. There is a heat exchanger in there, which is like a radiator. So we pump around hot coolant, and it loses its thermal energy store by heating to another pipe, which then takes the energy away and goes to a steam turbine or generator, and a transformer in the steam pressure turns the turbine, which connects to the grid, which produces electrical energy, or by an electrical process. Now, the other trendy idea is that we can have nuclear fusion. While fusion happens in the sun, but actually, fusion is a process where smaller nuclei make a larger one and release energy inside a star. And fusion is much harder to achieve than fission, as you have to overcome very strong electrostatic and proton repulsion. You have to push them very close together using pressure and temperature with fast-moving particles with a lot of kinetic energy until the neutrons take over and glue them together with this thing called the strong nuclear force, which you don't need to know at GCSE, but it explains why you can make these nucleons push together and stick. So if I get them close enough, it's sort of like a bit of an elastic thing that pulls them just together and binds them. You need to have an idea of some of the equations as well. So here we've got a fusion equation where two hydrogen make a helium. All of the protons and neutrons are accounted for, or two helium in this case make a bigger helium and two hydrogen. So you have lots of these processes going on in a star, which is just natural, and we're trying to do that on Earth in a fusion reactor. And you can see here we've got two examples for typical fission equations where a neutron has come in and hit uranium, producing then this barium krypton plus 3 neutrons. On this case, though, this is the same one, but this time we've got xenon and strontium and 2 neutrons. So you can't learn one, you've got to learn the idea. And again, it would be a fill in the gaps type question. So that is fission and fusion.